In this video, we will introduce the process of finding the maximum and minimum values of a function of two variables. We'll spend a few minutes first recalling what these results look like for functions of a single variable. Remember this application long ago that you did in Calculus 1, where a function of a single variable f of x was given. And your goal was to find the maximum or minimum, or the so-called extreme values of the function. This is just a very brief recap of that whole process. Here's one important thing I wanted to remind you about that. I won't go over the definition of max or min value for functions of a single variable because we'll do that in detail for functions of two variables in just a moment. But I did want to remind you of this. Remember that if f of x naught is some maximum value, then you can see from this picture that the derivative of f at x naught looks like it should be 0. So there is some connection between extreme values and 0 derivatives. But the derivative doesn't have to be equal to 0, because we could also have some situation like this. Whatever function this may be, it looks like this function has a maximum at this point, but this derivative isn't even defined, dne, right? So if you'll remember, what we did is we defined an object called a critical point, and we said that x naught is a critical point if either the derivative is equal to 0 or if the derivative did not exist. Either of those conditions gave us what we call a critical point. We'll do something very similar now for functions of several variables. Let's look at the definitions. The first important definition is this. We say that the function f of xy has a local max at a point a comma b if f of ab is greater than or equal to f of xy for all xy near ab. The picture looks something like this. So in this picture we have the graph of some function z equals f of xy, and we see at this point a comma b that it looks like, at least locally, the function attains a maximum. That is, as long as we stay within a little neighborhood of a comma b, the function is as big as it gets within this neighborhood. Now it may be the case that elsewhere in the function, for some other value, x naught, y naught, maybe we obtain a bigger value. But again, this is a local property. We say this is a local maximum. Intuitively speaking, a local maximum is just a local hill in the graph, even though the graph may go on I don't know, look like a mountain range, which is much greater elsewhere. And we have a very similar definition for a local minimum, or a local min, as we'll call it. F has a local min at a comma b if f of a comma b is less than or equal to f of x comma y for all x comma y near a comma b. I didn't finish writing out the definition, but it looks just like the one above. So similarly, a local min may look like a small valley in the function occurring at a point a comma b. Our goal for this section is simply, given a function of two variables, to find all of the local maxima and all of the local minima. Together we call these two kinds of points, or two kinds of values, I should say, the extrema of the function. So our goal then is to find the local extrema of a function of two variables. To see how this is done, let's begin by supposing that f has a local maximum at some point a comma b. Well, there are two ways this can happen. Roughly, either the function is differentiable at that point, or it is not. Let's suppose, for case 1, that the function is differentiable at that point. That is, that the function has a well-defined derivatives in the x and y directions, or in other words, that the partial derivatives are defined at that point. So if this is the case, then At that local maximum, we can see that both the x and y partial derivatives are 0. Here I've attempted to draw with these arrows the partial derivatives at these points. This is just another way of saying that the tangent plane should be horizontal at a local maximum. So case 1, if the partial derivatives exist, we conclude that partial derivatives must equal 0. That is, f sub x and f sub y evaluated at a comma b are both 0. That's case 1, and it is a straightforward generalization of the single variable case that we reviewed briefly above. And in fact, we're not proving any of this here, but this single variable case is used to prove that this is one of the cases where local extrema occur. So this is case 1. But there's something else that can happen. Perhaps the function isn't even differentiable at that point. That is, perhaps partial derivatives don't even exist. So case 2 might look something like this. Perhaps part of the graph bears some conical shape. I don't know what the rest of it looks like. Doesn't matter. It looks like it's possible here to have a local maximum at a comma b, but if this is what the graph looks like, then we can make a pretty good case that the partial derivatives don't even exist there. So case 2 for local maximum is that either the x partial derivative or the y partial derivative, or perhaps both, doesn't even exist. So we'll summarize and write down the theorem in just a moment. The summary is there are 2 ways that a local maximum can occur. Either both partial derivatives exist in R0, or at least one of the partial derivatives doesn't even exist. And the same is true for local minima as well. So now we can summarize all of these results in the following theorem. The theorem looks like this. Suppose the function f has a local extremum, that is either a local maximum or a local minimum at the point a comma b. Then one of 2 things are true. Either 1, both partial derivatives evaluate to 0, or 2, the x partial derivative or the y partial derivative doesn't even exist. One of these 2 things has to happen at any local extremum. I'll just note that in practice for us, it's usually more often than not the first case that occurs. So this gives us a strategy for finding the local extrema. We find all of the points where the first and second partial, we find all the points for which the x and y partial derivatives are 0, or we find points for which at least one of these partial derivatives doesn't even exist. These points which satisfy these conditions come up a lot, so we have a special name for them. We call them critical points. We say that a point a comma b is a critical point if one of these conditions are true. If either both the x and y partial derivatives evaluate to 0 at that point, or if one of those partial derivatives evaluated at that point doesn't exist. And again, I'll repeat it one more time. To find the local extrema, we find first critical points. Let's go on and do an example. Here's our example. Let f of x comma y equal the function x squared plus xy plus y squared plus y. Let's find all local extrema. So we'll begin by finding the critical points. To find critical points in turn, we need the x and y partial derivatives, so we find those. The x and y partial derivatives are 2x plus y and x plus 2y plus 1, respectively. So how do we find the critical points? Well, we set both of these equal to 0. And in so doing, we've introduced a system of 2 linear equations in 2 variables. So we can solve this thing by substitution or elimination. So I can write this as 2x plus y equals 0 and x plus 2y equals -1. Now, let's solve the system. I can multiply the second equation by -2 to obtain -2x minus 4y equals 2, and then I add these vertically to eliminate the x, which gives me 3 negative 3y equals 2, or y equals negative 2/3. And now I can substitute this into either above equation to obtain a solution for x. And I obtain x equals 1/3. Note that the partial derivatives fx and fy are just polynomials in x and y, and so they're defined everywhere. There are no critical points of the second variety, those where the partial derivatives are undefined. There's only one critical point of the first variety, and that critical point is 1/3, negative 2/3. So we have some local extremum at 1/3, negative 2/3, perhaps. But we don't know if it's a local minimum or a local maximum, or if something else happens. Let's go back and re-examine what can happen at a critical point and see if we can devise some test to tell us if we have a local minimum or a local maximum. There are three things that can happen at a critical point. One, the function can have a local maximum. Two, the function can have a local minimum, or neither of those things may occur. It's possible that the function has what we call a saddle point, which is this sort of center of a saddle right here. And if you look closely at this picture, which is a pretty poor picture, maybe I can do a better job. Here's our saddle. If you look closely at the center of a saddle, you may be able to convince yourselves that the tangent plane is horizontal at this point, but there's no local maximum and no local minimum. So, the existence of a critical point does not guarantee a local extremum. Local extremum would happen here or here. There is a third possible thing that can happen. We can also obtain a saddle point at a critical point. So let's go back and review the process. Finding critical points is the first step to identifying local extrema. After we find critical points, we need to determine which one of these three possibilities occur at the critical point. We'll do that in the next video.